Hi, my name's Irene, and here's my presentation for Lab 2 on projectile motion. So, the purpose of this lab was to track and understand motion of a projectile. We also observed Newton's second law to see how different forces can affect projectile motion, and um, we were able to model this fundamental principle with Tracker, which allowed us to get an accurate position versus time graph and a velocity versus time graph. The fundamental principles we used were Newton's second law, momentum, and the position and velocity update formulas. From this lab, we learned how to find the ending velocity and position by using an equation from Newton's second law. All right, so here are just some of the fundamental principles. First is Newton's second law, which is the velocity update formula, and then we also use the position update formula, and then gravitational force near its surface, and then lastly, the drag force formula. So here are some key ideas of this lab. First is that gravity and drag are the only two forces acting on the system. And then the ball of paper has an initial velocity of 0 because the ball starts at a resting position. And then all tracker markings are at the exact center of the object, and then the ball starts at exactly 0 on the y-axis. Also, most importantly, it's good to know that the system is the ball of paper, and then the surroundings is everything else around it. All right, and here is our tracker analysis. All right. And then here is just some data we got from the tracker. So it was 0.067 seconds per frame. Our observed start time was 0.833 seconds. And then the object's initial position is 7.78 or 98, and then 1.342, and then 0. And then the object's initial velocity is 0 meters per second. And then here is the code we used to show the initial conditions on GlowScript. And then for the computational model, here we used the velocity update formula and the position update formula. And then also Fnet is equal to force due to gravity, shown to the right. And then this is how we did the iteration part of the computational model. And then here is the computational model arrows. And then for our GlowScript results, we got these two graphs. The graph to the left shows position versus time, and you can see a downward trend with that graph. And then the graph to the right shows velocity versus time, which also has a downward linear trend. And then from the code, we were able to get two graphs that show velocity versus time and then position versus time. The blue line shows the x direction, and then the red line shows the y direction. And then here are just some possible errors that could have occurred in the lab. There could have been some outside forces, such as the AC blowing air, which could have affected the motion of the paper ball. And then Also, the paper ball that was thrown was not a perfect sphere, so that also could have affected the results. And then lastly, our video might have been recorded at a slight angle, which also could have affected the results. So from this lab, we can conclude that we can use Newton's second law to determine the net force acting on an object at any point. Especially for a projectile, this helps us determine velocity and position in both the x and y direction when a constant force is acting on the projectile. And then further questions, what does it mean? So terminal velocity occurs when the upward drag force balances gravity, making net force zero. Without the drag, objects will keep accelerating so no terminal velocity is reached. With drag, the object eventually falls at a constant velocity. A way to test this is by dropping objects with different shapes to see how drag affects their terminal velocity. And then for the what if question, if the object was thrown straight up without drag, it takes equal time going up and down, so total time is double the ascent time. And then with drag, it will slow down more on the way up and reaches the terminal velocity on the way down. This makes the total time longer than without the drag.